This video is about projectile motion, but we're not going to go through a bunch of problems with the numbers in a way that you might have seen before. Like a ball is launched at 20 meters per second at 60 degrees above the positive x-axis, and then go solve for everything. In fact, with this amount of information, ignoring air resistance, you could figure out every little bit of the subsequent path of the particle. You would know where it's located at any moment in time. You would know how high it gets or its maximum height. You could figure out its horizontal range, the horizontal distance from where it was shot. You could figure out the total flight time while it's in the air. You could figure out how fast it's going at any location, construct a velocity vector at any moment in time, and fully analyze the problem, right? But what I want to try to argue here for you and help you get to is to realize that there's so much more than the numbers in this problem. And we're going to get a chance again to look at this major process of starting with first principles, things that we know are true in physics, and then working all the way up to some representations of this system more abstractly that really allow us to understand what's physically going on. I think you'll find a lot more depth to this than your standard problem. Now, it is very important as a beginning physics student to make sure you can also solve a problem like this, using the numbers. That might be a good starting point to make sure you're getting the basics down. But very quickly, you want to get to this next level where we're really understanding deeply and conceptually what's going on in this problem. Now, before we get to that higher level, I want to point out one thing that I'm going to do in numbers to give it some context here for you. And that is that the initial velocity vector, which is a really important piece of information in most projectile motion problems, is a mathematical object. It's a vector, okay? And it has a horizontal component and a vertical component. And I always recommend drawing that over to the side away from the physical picture of the path. So for example, this here would be the initial velocity vector, and I could break that down into components. My horizontal component of velocity and my vertical component of velocity. And I would label this as the initial x velocity and the initial y velocity. Of course, this angle here would be about 60 degrees. If I were to put the number, I'll just put theta actually, just keep it general for now. And that triangle that you're seeing with the hypotenuse and then obviously two sides has nothing to do with this picture here. This is a picture of the physical path that the ball takes through space as it's launched and it flies through the air. Over here, this is a breaking down of the initial velocity vector into horizontal and vertical components. And it's really important that you never try to draw this picture here of breaking down the velocity vector on this picture of the physical path, because you can confuse yourself with what you're doing. Okay, so always separate that out over to the left. So if you were working in numbers here, you would find using cosine and sine that the initial horizontal velocity is 10 meters per second and the initial vertical velocity is 17.32 meters per second. So you should be familiar with that in terms of sine and cosine. In fact, I'll just write out here that this would be the initial velocity or the magnitude of the initial velocity vector times the sine of theta. And this would be the magnitude of the initial velocity vector times the cosine of theta. And oftentimes in solving these problems, we will rewrite this and we'll just put a v here. And then in the back of our minds, we're remembering that v stands for the initial launch speed. Okay, so maybe I'll make a little note here to myself. V stands for the initial launch speed. So it would be this part, just the magnitude of the velocity vector. If you wanted to be very formal about that, you could write out the magnitude of the initial velocity vector. But you can see how cumbersome that is to have to write down and use in an equation. So oftentimes, like I'm saying here, we're seeing that we're just going to use v for that. Okay. All right. Now, moving forwards, we could solve this whole problem out, like I said, with the numbers. But instead, let's try to develop some relationships that exist. And I want you to think about Like, what are some important parameters for the motion of this object? Like, what would we want to be able to calculate? Think about that for a second. And hopefully you're thinking that time is something that's really important. Time is always kind of a glue that allows us to go between the horizontal and the vertical quantities in these types of problems. So if there's some way to like figure out what the amount of time that this object is in the air for depends upon, that could be pretty helpful. So let's do that. So I'd like you to pause the video right now, and I'd like you to think about it, maybe just list a few things out. I'll write this out here. What do you think the total flight time depends upon? Total flight time. What does it depend on? All right, pause the video and list out a few things, and then we'll see. So I've listed out a few things that you might have thought about. Launch speed is one that makes sense conceptually. If you launch it up a lot higher speed, you could reason that it would probably take more time to fly through the air. Maybe if you launch it at a higher angle, it would take longer to fly through the air. That certainly makes intuitive sense. And then gravitational field strength. If we were on a planet with very little gravity, you'd launch it up into the air at some speed, and it would take a long time for that thing to come back down. So these three things seem pretty intuitive. So what we're after then, of course, is some type of expression or formula. We have flight time over here. That's what we're trying to predict. And we're trying to see what it depends upon. So there's going to be some stuff over here, and we're proposing maybe these three things end up in our final result. Maybe not all three of them will. Maybe there's more things, but it's a good start to map out intuitively what you're thinking to give you a guide for what might go here. All right, so the next idea would be, well, let's identify our first principles. What are things that we know are true? What are some major concepts that apply to this problem? And what are some fundamental equations that allow us to write things down mathematically? So pause the video and write out as many ideas that you think are relevant for concepts here, and then write out an equation. And I'll give you a hint. There's really just one equation that will get us to where we need to go to start with here. So see if you can figure out which equation out of our equations of motion makes sense here, and write those down on your paper. All right, go ahead, pause the video, and identify first principles. So I've listed out a few major concepts. Horizontal and vertical motion are independent. Gravity causes the vertical acceleration. And we have constant horizontal velocity since there's no horizontal force at all on our particle. And then down here is what I call the second equation of motion. And I've written that one down, and we're going to now work with it. So the next step is to figure out how do we solve for what we need to solve for. And again, just to remind you, it was flight time. So what does that even mean? Total flight time. Think about that for a second. Where would you set your initial point, and where would you set your final point? Well, I've kind of given you a big hint here. And I would put my initial point right here when we launch the object, and my final point all the way over here. Okay, perfect. All right, now let's also make sure we remind ourselves of our coordinate system. We'll use the standard XY plane, where this is positive and this is positive in the X direction there. All right, now we're about ready to go. I'd like you to pause the video now and see if you can use this equation right here and whittle it down. There are some things you can do to it in order to solve for the flight time. Okay, and see what you come up with. You may not get to the exact result that we're going to get to in the end. You might get to an intermediary result, but just work with this as best you can right now and see what you can produce for the flight time. Go ahead, pause the video and try that. Now, an important discovery in this problem is that when you hear the phrase total flight time, you need to turn that into kind of a picture where you're looking at the whole path. And when you do that and you start labeling that picture with symbols like initial y position and final y position, you start to see how, oh, they're equal to each other for the total flight time. the final y position, the final vertical position, is identical to the initial vertical position. That's a huge fact here because it's going to allow us to use our second equation of motion in a simple way. So now what we can do is we can subtract over y initial, and we'll just leave everything else the same for a second. And if they're the same vertical positions, this just cancels to 0 right there. That's going to make the math a lot easier. I'll leave off the units for the 0. Then we need to remember our coordinate system. Down is negative, up is positive, and we've learned before how to deal with that with the gravitational field strength. So we'll plug in minus g here for our vertical acceleration, t squared. And then we do have initial vertical velocity, most definitely. We're shooting this up at an angle, and here's the initial launch speed, v, and we're breaking that down into initial horizontal and initial vertical, like we said before. And that's our angle theta. All right, we'll come back to that in a little bit with the components. Now, continuing along with the math, you should be able to take it from here. So go ahead and now solve for the total flight time. And to be real specific, I'll put a little FL here for flight time to give us, or to communicate more information about what this time actually represents now that we've made this assertion over here. All right, pause the video and solve for the flight time, see what you come up with. All right, here's the solution. So let's just quickly step through it. And we're just doing algebra here, so hopefully it's easy for you, but you would move this over to the other side. You got a minus sign there, it becomes a positive. And then you could cancel out the squared with this whole t of flight time term there, or just divide over t flight time, and that'll cancel it out as well. It's the same thing, but it's nice to be able to just quickly kind of cancel things out like that with your algebra skills. And then we solve for the final flight time, and we get 2 times the initial vertical velocity divided by the gravitational field strength. So incredible. Now let's extract out of this the relationships. What are you noticing about what the total flight time depends upon? Okay, pause the video, and it should hopefully be easy for you now, but we'll write those over here. The total flight time is proportional to 2 things, and let's extract those specific relationships and write them in our proportional notation. Go ahead and try it. All right, so hopefully you were able to get it. And we see that the flight time is directly proportional to the initial vertical velocity. Not the horizontal velocity, but the initial vertical velocity. It's also key to realize that it is the initial vertical velocity, not the vertical velocity at some point along the path. Also notice that it's not the initial launch speed. What was that? Well, that was the hypotenuse of this triangle, if you will, or the magnitude of our initial velocity vector, which was the number 20 when we were looking at it in numbers. So this term here is the initial vertical velocity, which would be represented by that side of our triangle and our breakdown of the velocity vector. The other relationship is the inverse relation of flight time with the gravitational field strength. Hopefully that makes sense to you. The stronger gravity is, the larger g would be, the smaller the flight time, and vice versa. Now if we go back to our list of things that the flight time could depend upon, we certainly have checked off gravity from our list. We see it right here. But I don't see the launch speed or the launch angle in this equation. I see the initial vertical velocity. That's not the launch speed, and that's not the launch angle. But there is a way to get to these 2 things, which is a hint I'm giving you here. So my question to you now is pause the video and see if you can transform this into something to do with launch speed and launch angle using the symbols that we saw in the beginning of the video. Pause and see if you can do it. All right, to do it, you need to draw out the initial velocity vector, which I've done here. And then for notational simplicity, we are calling the magnitude of that vector just lowercase v, and that is the launch speed. And then the launch angle is represented by theta. So I'm doing simple trigonometry and knowing about how to break these vectors down into components, we realize that we have v sine theta for the initial vertical velocity, and we have v cosine theta for the initial horizontal velocity. Now we're good to go. We'll go ahead over here and we'll plug it in, and we get that the flight time is equal to 2 times the launch speed times the sine of our launch angle. Interesting. And then divide that by g. And then we can put a box around this. So now we have some relationships. We can check these off our list, and we can see that there's a direct proportion with flight time and launch speed. Interesting. We can see again the inverse with gravity. And then finally, we have a proportion with the sine of the angle that we launched this thing at. And we'll just assume angles launched between 0 and 90 degrees. Cool, so we're seeing our first instance of sine or cosine showing up in a formula. Now let's see what this really allows us to do. We're not going to get bogged down in plugging a bunch of numbers in. We're going to compare two scenarios now that we have this advanced level of knowledge about this flight time idea. The question is, we have two objects that are launched at identical angles above the ground level. One of them is launched at 20 meters per second. The other one's launched at 60 meters per second. I'm not even going to specify the angle, but I am giving you the numbers for the launch speeds, 20 and 60 meters per second respectively. And my question for you is to compare the flight time of B to the flight time of A. So by what factor is B's flight time greater than, less than, or equal to the flight time of A? All right, so go ahead and figure out what goes right here. There's some factor, and you have all the information that you need from this specific equation and the relationship you can extract from it. Pause the video and see if you get this. All right, well, we got the direct proportion between flight time and launch speed, assuming the angle is constant, assuming the gravitational field strength is constant between the two scenarios, and we apply that thinking, and we see 3 times as much launch speed, and we therefore know immediately that object B will spend 3 times as much time flying through the air. That's pretty cool, and we did not have to get bogged down in a bunch of calculation. Let's do another one now where we keep the launch speed the same, but we vary the angle. This will be our first instance of where we're using some trigonometric function in our proportional reasoning. So pause the video now, same question. Compare the flight time of B to the flight time of A. By what factor will the flight time of B change compared to A when we take our object and instead of launching it at 60 degrees, we shallow the angle out and we only launch it at 30 degrees for the same launch speed? Pause the video and try it. All right, so let's take a look. Now for this one, it's a little bit subtle, and I want you to watch out for something because you've been seeing me do certain things like, for example, maybe distance is proportional to the square of time, and then I say, this is just for like a one-dimensional problem, I say, hey, look, let's take time and double it, and then proportional reasoning would say that it's going to go 4 times as far because we do the operation that is said, and we square 2, and then that would give us 4 times as much distance as an example of that process for proportional reasoning, right? Well, when we're dealing with sine here, we got to be careful. That's not going to really work for dealing with these angles. So, if you go from 60 degrees to 30 degrees, that's essentially like cutting the angle in half, right? So theta is going to, as an angle, to 1/2 of theta. But if you try to take that reasoning and then take the sine of 1/2, this in no way is going to get you to the answer at all that you need to get to. So that's kind of breaking down with these trigonometric functions. So instead, we'll just do it the formal way instead of that little shorthand way by taking a good old-fashioned ratio. So, we'll write down the flight time of B, and we'll divide that by the flight time of A. Of course, that would equal 2v sine theta of B and divided by, and then of course that's divided by g. Sorry, gets a little bit messy here. And then we'll divide all of that by 2v sine theta of a, and that's also over g. All right, so you can start canceling a bunch of stuff out. Of course, that g would cancel out with that g. They're launched at the same speed, so these v's up here and the 2 would cancel. And lo and behold, we get a ratio of the flight times. And we'll expand, or we'll bring this other thing onto the other side. So we'll get sine of theta b over sine of theta a multiplied by the flight time of a. Perfect. So now all we have to do is take this ratio of the angles, the sines of the angles of the two, and then we'll get the right result. So let's do that quickly. I'll just kind of write that over here for the sine of the angle. So we got sine of 30 degrees divided by sine of 60 degrees. And I hope your trig skills are quick enough to where you can just know to write down sine of 30 is a half, and sine of 60 is the square root of 3 divided by 2. 2's cancel, and then we end up with a ratio of 1 divided by the square root of 3. And you probably wouldn't want to leave it like that. You want to multiply it all out. So if we do that, and you take the square root of 3, it's about 1.73, and then go 1 divided by 1.73. So I'll do that right now. 1 divided by 1.73 gives me about 0.578. Cool. So we'll write that out here now finally, that the flight time of B is equal to 0.578 times the flight time of A. Interesting. Cool. So it's not like exactly cut in half or anything like that. And it's because of the way the sine function behaves mathematically. Awesome. So to conclude the video, you see we've done so much more than numbers here. We've really kind of looked into this system to find out exactly what affects the amount of time this projectile is flying through space for. And we've seen that it's about the launch speed and the launch angle, which together are all encapsulated in the initial velocity vector, as written out in text here. And then, of course, the gravitational field strength. And what got us there was not by getting caught up in a bunch of numerical calculation, but the process. First principles, identifying concepts and fundamental equations or laws that we can then use to derive these results that help us understand our system and help us kind of reveal the story of what this system is all about and what parameters we can change and how those parameters affect other things. So to leave you here, why don't you, on your own time, try to do everything we've done in this video here for flight time, but do it for the horizontal range. What do you think affects the horizontal range? Can you do this whole process from start to finish and come up with your own theoretical model? I think you can, and it's a great challenge. So try that, and we'll see it in a future video. And then likewise, the maximum height, we've already seen that in 1 dimension, and you could try it again here in 2 dimensions. It's a little bit easier than the problem about the horizontal range. All right, with that, I hope you enjoyed this video and learned a lot more about how we get up to the next level beyond numerical calculation to truly understand what is happening in these systems. Take care, and we'll see you next time.